Hello calculus students, time for another video lesson. I'm going to do some things with the calculator that take a little bit more time than we have for class, and I want to be sure to get through the lesson and the calculator demonstrations. So please copy this in your warm-up book. This problem, first problem, is one like that was in the previous homework. I didn't do an example of it in class. I wanted to see if you could kind of struggle through it a little bit, but it is one that AP loves. So AP loves this type of question, and they use it in lots of different places, and this is just the first one that you've come across where they're testing the product rule and the quotient rule without a function. So you are allowed to assume that U and V are differentiable functions, which means, of course, if it's differentiable, remember, differentiability implies continuity, but not vice versa. Continuous does not imply differentiability, think absolute value, but differentiability does imply continuity. Think differentiability, think smooth, not just continuous, but smooth. So those are the assumptions you're allowed to make. They don't have to explicitly mention them. But using the product rule here for U times V for y1, so if I want the derivative with respect to x of the function y1, normally we don't put parentheses around that, at x equals 4, because notice they can't ask me for a rule. They didn't give me a rule for the functions. I can't find a derivative rule. So this never changes. First function times the derivative of the second plus the second function times the derivative of the first. First function, derivative of the second, plus second function times the derivative of the first. So the first function at 4 is U. The derivative of the second function V at 4 is -1, plus the second function at 4 is 4/3, times the derivative of the first function U at 4, which is 1/5. Now you've done the product rule. You have to get, if this is not multiple choice, you have to get credit for part of this because you've done the product rule. So of course this is 3 and 4/15, which you can write as 3 and 4/15, or you can write it in, what is that, 49 over 15. Don't care which version you give me here for a final answer. If you're writing it on multiple choice, most likely 49/15 would be there. Now let's do the derivative with respect to x of y2 at x equals 4. So y2 is a quotient. I cannot just take the derivative of u and the derivative of v and divide them. That's the trap they're laying for you. Same with the product rule. Asking you for the product rule of u times v, and if this is multiple choice, the correct answer of 49/15 would be there, but so would be whatever the derivative of u is, 1/5, times the derivative of v, so -1/5 would be one of the answers to see if you fall into the trap of just like, oh, the derivative of a product is the product of the derivatives. No, the derivative of a product takes the product rule. The derivative of a quotient takes the quotient rule. So since y2 is a quotient, then I need the quotient rule, which again never changes, right? This is high over ho. So the derivative is ho, which is the bottom function 4, bottom function v at 4, ho d high, so the derivative of the numerator at 4, minus high d ho, so this, the top function at 4, and I lost track. Ho d high minus high d ho, so the derivative of the bottom at 4 all over the value, not the derivative, just the value of ho squared. Again, you've done the quotient rule, clean it up a bit. What is that? 4/9, 4/15 minus 3, because that would be minus a positive 3, and 3 would be, what, 45/15? And that's all going to be divided by 16/9, which of course means it's all being multiplied by 9/16. So what is that? Negative 41/15 times 9/16, whatever the heck that is. Who actually cares? Blah. Right? But that's what they're testing you on. Do you know the product rule and quotient rule in theory? Not its, application of function. You're not actually getting a function rule. They're just testing to see if you know it. They don't actually care that it's 49/15 or whatever this blah is, right? They just care, can you use this information and tell me how to use the product rule and the quotient rule. Okay, so yes, I found y prime at 4 using the product rule, and I found y prime of y2 at 4 using the quotient rule. Alright, now we're going to look at number 2. Find the tangents, so that's the equations, to the curve x cubed at the points. Looks like maybe there's more than one. Whoops. X comma y. Where the slope, which is this derivative, but right? The slope is the derivative, equals 4. And we'll worry about this part later. So, tangents to the curve at the points where the slope is 4. Now, look at this, right? Look at this cubic function. I know it increases because the leading coefficient is positive. Don't you agree that all the slopes are positive? Slope here, tangent line positive, tangent line positive, tangent line positive, tangent line positive, tangent line 0, tangent line positive, tangent line positive, tangent line positive. All tangent lines have slopes that are greater than or equal to 0. So certainly there is a slope of 4, right? So how do I find the slopes? Right? The derivative. So if y is equal to x cubed plus x, y prime must be equal to 3x squared plus 1. And what do I want the slopes to be? These are slopes at every x on that x cubed plus x. Remember, I want the slopes to be 4, so go ask the derivative. Excuse me, derivative. Oh, I meant to change colors. Excuse me, derivative. I want you to be 4. Subtract 1 to get 3, divide by 3, get 1. If you just tell me x is equal to 1, well, you're missing something, right? How many things can you square and get 1? Plus and minus 1. So I can already fill in this information. When x is negative 1 and when x is 1, there will be slopes that are 4, because the derivative was set equal to 4. Hey, remember this information here where I said that all tangent lines have a slope that is greater than or equal to 0? Well, look at the slope generating rule. 3x squared plus 1. Isn't that a function whose graph is always positive? Remember, at every x value here, the y value, the range, are the slopes on y. So, at the point negative 1, 4, and the point over here, 1, 4, Those are not the points on x cubed plus x. They are points on the derivative that say when x is -1, the slope on x cubed plus x is 4. When the at the x value 1 on x cubed plus x, the slope is 4. So do not put that 4 here or here. This is asking for the points on x cubed plus x. The derivative is 4 there. The slope is 4. So over here on x cubed, somewhere here where x maybe is -1, and over here where x is 1, the slope is 4. So I want to show you what that looks like on the calculator. So there is, in y1, you see x cubed plus x. And I'm going to shrink my window just a little bit. Let's make this -5 and 5. So let's do this. Trace. At -1, y is -2. And remember that cute little draw tangent thing I asked you about? Draw the tangent line at -1, -2. There's the tangent line. Look what its slope of the tangent line is. 4. How about let's do the same thing at 1. Draw the tangent line on the graph x cubed plus 1 where x is equal to 1. What's the slope of that tangent line? Also 4. Hey Algebra 1 kids, what do lines with the same slope look like? Yep, you got it. Parallel. Do you see the two tangent lines? Both of their slopes are 4. And remember what points those were at. When x is -1 on the graph x cubed plus x, y was -2. So -1, -2 on x cubed, slope was 4. But also at the point 1, +2, the slope of the tangent was also 4. So I answered this question. Check. Right? The points where the slope is 4, but don't forget they asked me for the equations, right? The equations of the tangent line, and let me write those down here, would be y minus blank is equal to 4 parentheses x minus blank, and y minus blank is equal to 4 because there's 2 points, and you're going to put -1 and -2 here, and +1 and +2 there, and of course clean up these negatives. So if I got this into mx plus b form, which you don't have to, it would be y is equal to 4x plus 4, and then of course minus 2, which would be plus 2. And then this one would be y equals 4x minus 4 plus 2, which would be minus 2. Cool? Now let's go back to this. What is the smallest slope on this curve? The smallest slope on the curve is, right, if all the slopes are tangent, or are positive, remember we said that here, and then look at the graph of the derivative, look at the range. What is the range of this parabola? Right? The range of this parabola is y coordinate of the vertex to infinity. So what is the smallest? But remember, since this is the derivative, this is actually y prime values. What's the smallest y prime value? The smallest slope is 1 when x is 0, right? This is the lowest value on the derivative graph, and it's when x is equal to 0, y prime, right? This is y prime. Label my x's. When x is 0, y prime is 1. But what graph are they talking about? This one. Alright, let's go on. So we are going to be talking about the this idea of the derivatives and graphs of the derivatives with specific units on our axes. So consider a graph of displacement, which is just distance versus time. Notice my units here. Distance in miles, time in hours. So here's a random graph of my distance versus time. Average velocity, which is the slope of a secant, can be found by Algebra 1. There's point A, there's point B. What is my average velocity between point A and B? Change in time compared to the change in distance. And we're just going to call S distance. Change in position, which is delta S, compared to the change in time, which is delta T. So this says the, I don't know why, really, shouldn't this be a G? Y average, the velocity average. Now remember, it's only called velocity because of these units. Miles per hour. So, what is the change in position? Well, it is the position function at a specific time plus a small amount. Small change. Right here is my 1 time, and here is my, right? So let's say this is 2, and let's say delta t is 3, then 2 plus 3 would end me at 5, right? So f of 5 minus f of 2, for example, all over 5 minus 2, which shocker is 3. That is my velocity average. But as you can see, as in calculus, we haven't been interested so much in average, we've been interested in instantaneous. So, velocity, the velocity function is the derivative with respect to time, right, of position. And of course that definition is a limit as delta t shrinks to 0. So wait a second, you think about what that means? Velocity is the first derivative of position. What? Crazy. Hello, physics. Speed is always positive, right? You don't talk about going negative 50 miles an hour, but you do talk about having a velocity of negative 50 miles per hour. Right? Absolute value means, right, positive. Because velocity indicates direction. If I'm talking about going right or left, positive velocity would be going right, negative velocity would be going left. If I'm talking about going up or down, positive velocity would be going up, negative velocity would be going down, but my speed would always be positive. So here's a freefall equation problem like your book would have. Your book kind of assumes that you know this physics formula, AP will not assume. AP, on the AP exam, they will always give it to you and they'll tell you what your gravity constant is. If my gravity constant is 32, I know from physics that I'm dealing with feet, measuring in feet and seconds. Again, that's not something AP would expect you to know. They'll tell you that. So my position freefall equation is negative 16t squared, where again my distance is in feet and my time is in seconds. So then, what is the velocity of freefall? It is the derivative of position, which is of course bring the power down, subtract 1 from the exponent. Well, then acceleration is the derivative of velocity. What? Ooh, see that rocket take off? Rockets, get it? Acceleration is the first derivative of velocity. Right? The first derivative with respect to time of velocity. But that's the second derivative of position. Crazy. So in our example, velocity was negative 32t. How do you take, remember that's t to the first, how do you get what's the derivative then? Right, power down, subtract 1. Acceleration is negative 32. I don't know why I have a period after that. Now, I've purposely left off all the units. If distance is measured in feet, what are the velocity and acceleration measured in? Now, I already gave you a hint on the graph that I had before. If velocity is a slope, right? It is slopes of the position graph. Then it is and the slope is change in y over change in x. It's just that my y value is feet, position, and my x value is seconds. Acceleration is the slopes on the graph of velocity. And the slopes would be, again, change in velocity compared to change in time. But so the units on velocity are feet per second, so the change in velocity are feet per second compared to time. So I took algebra 1, right, and I know about complex, right, fractions. Feet per second divided by second is feet per second times 1 over second, which is of course feet per second squared. OMG. Sorry. So the relationship, how AP really, now again, this is physics, but just AP calculus is only going to test you on a little bit of physics. So again, here's a random, not the same one that I did before, just a different distance time graph. And I want you to look at concave up, linear, concave down, linear, concave up, constant. Let me repeat. Concave up, linear, concave down, linear, concave up, constant. Let me break this up. So, can you look at this spot and talk to me about the tangent lines before? Aren't the tangent lines starting low and getting higher and higher and higher and higher? Since the slope is velocity, we say the velocity is positive and increasing. Now remember, acceleration is the derivative of velocity. So it's the derivative of the slopes. Well, if you were to graph all these increasing tangent lines, write the values. So let's say 0, 1, 2, slopes 3, slopes 4, slopes 10, slopes, whatever. The acceleration, the derivative, would also be positive. However, on this linear piece, the slope is constant, but positive. And if the slope is constant, the derivative of the slopes would be 0, because the first derivative of a constant is 0. Look at this next piece. Velocity is positive, right? But decreasing. If the slopes are decreasing, the second derivative will be negative. And then, of course, at the turning point, instantaneous horizontal tangent means the slope is 0, and if the velocity is 0, well, so is acceleration. At the next piece, I'm still concave down, but I'm past the turning point. Notice that my slopes are now negative. If the slopes of the curve are negative, but they're getting more and more and more and more and more negative, the velocity is decreasing, which means if the slopes are decreasing, the next derivative, its derivative, will be negative. Here's another constant piece. So this time the acceleration is still going to be 0 because velocity is constant, but velocity is negative. In this little concave up piece, the slopes are negative, right? Negative tangent line, but coming back towards 0. So if your slopes, the velocity, are negative, but they're increasing, they're coming back towards 0, then the slopes of the slopes are positive. So I want you to look at those 4 boxes. I have positive, positive, negative, positive, negative, negative, positive, negative. Now, Mr. Getz would be very annoyed if I talk about these as forces, but I'm just gonna. He's just gonna have to get over it. If you have 2 forces, if you have acceleration and velocity, both acting in the same, again, Mr. Getz, forgive me, direction, positive, positive, that means whatever you're talking about, the speed is increasing. But that's exactly what happens here. I know acceleration and velocity are negative, but they're acting together, not against one another. They're acting together. If they're acting together, even though they're in the negative direction, my speed is still going to increase. But if your forces are acting against one another, they're in opposition, and I don't care which one is which, negative, positive, or over here, positive, negative, my speed is going to decrease. Because they're working against one another. Think about that, right? Lesson in life. Work together, things go faster. Work against one another, you might still make progress, but you're going to go slower. Okay? Of course here, nothing's happening, right? Acceleration 0, velocity 0, your distance, time is going on, but your distance is staying the same. This is, again, I did this example. I don't want this example to freak you out. Hear me? Don't let this example freak you out. This is a book type problem. I have not seen AP give you something this nasty. But I think it's and it's not nasty calculus wise, it's just nasty algebra wise. But you're in BC Calculus, right? So I might do something like this on a test. So firstly, I was at Hawaii and I saw lava and it was amazing, except it wasn't shooting up, it was just oozing out of the earth. It was pretty freaking cool. Anyway, here's AP will always give you your velocity, you know, and free fall equations. Here, this is not free fall, right? Because the lava is shooting up in the air. So I have an initial velocity. So given a position equation where the position is an initial velocity times time minus 16, so I must be in feet per second, where the initial velocity is the exit velocity of a particle of lava, right? So exiting the earth, velocity is the highest, and then the velocity is going to shoot up in the air, and then of course gravity on earth is working on it, and so it's going to slow down and reach a maximum and come back down. So I do know the height of this is 1900, but that's feet, that's not a velocity issue, right? Well, if I say velocity is 0 at this height, right? Velocity is 0 at the height, right? Because the lava is going to go up and then come back down. I can at least solve this equation for t. Still got that initial velocity in it. Then I go back to my initial position equation. I don't know t. Oh wait, yes I do. There's t. And notice I can put in 1900 because this is at the time, this is the time at that maximum height when velocity is 0. So I just did algebra here, right? I now only have one unknown. VO, VO. I can solve this for VO. So I have VO squared over 32 minus 16 VO squared over 32. Same denominator, which is 30. I get a common denominator of 32 squared. That's just algebra, right? Square root both sides. This time I don't need plus and minus because I am just after the positive amount, and I have a calculator in my hand and I get this answer. So again, I really only did this example for some of your book problems. The AP exam will be more straightforward and more like the handout that I want you to pick up now. So the handout for practice looks like this. A particle moves along a line so that its position at any time t is greater than 0 is given by this function. Oh, it's quadratic, where s is measured in meters and t is measured in seconds. So this is meters and this is seconds. So sketch the original, the first derivative, which is velocity, and the second derivative, which is acceleration. So if I have s of t, which is t squared minus 4t plus 3, I know how to graph that from t greater than 0, right? 0, 3, it's going to come down, parabola opens up, come down like this, and go back up. Okay, that's a terrible drawing, but you get the picture. Picture. Mwah. Then I can answer this question. I know I haven't done the other graphs, but I can answer this question. Find the displacement, right? That's the change in position. So s of 2 minus s of 0. S of 2, plug in 2. 2 squared minus 4 times 2 plus 3, and I get negative 1, minus s of 0, which is 3, which is negative 4. Don't forget units. Right? Negative 4 meters. That means that the negative indicates direction, right? So if we are talking about a particle moving along a line, it's going right and left. So what does this negative 4 meters mean? The displacement means that after 2 seconds, the particle is 4 units left of where it started. Now let me do s prime of t, which is velocity. Power down, 2t minus 4. That's a linear function. Starts down here at -4. Hits the x-axis where? Yes, at 2. Hey, shocker, that's where the position graph had a horizontal tangent. And increases. Notice where the blue graph is negative, the red original graph is decreasing. Where the blue graph is 0, the red graph has a change in direction. Where the blue graph is positive, the red graph is above the x-axis, is increasing, excuse me. Find the average velocity during the first 4 seconds. That is a slope of the secant. So that is s of 4 minus s of 0 minus over 4 minus 0. But s of 4, oh, hey, wait, that's 3. Minus 3 over, who cares? That's 0. Don't forget units. It's not meters, it's meters per second. So, hey, does that make sense? From the average rate of change from 3 to 4, look at that. Slope of the secant, yeah, that slope is 0. But now find the instantaneous rate of change. That's the slope of the tangent. So what is b of 4, which is s prime of 4, right? Before that took a limit to do, not anymore. I have the rule. What is s prime of 4, which is v of 4, which is 2 times 4 minus 4, which is 8 minus 4. I think that's 4, right? Don't forget units. So, at 4 seconds, not an average, at 4 seconds, the particle is going 4 meters per second. Now, before I turn the page, I'm going to draw. Do what? Orange. Green. I didn't find the acceleration, so s double prime of t is equal to the first derivative of velocity, which is equal to acceleration. Oh, that's a terrible looking t, isn't it? I mean terrible looking a, which is a of t. Oh, I ran out of room. But remember, since the velocity is linear, the derivative of 2t minus 4 is just 2, a constant function. So starting at 0, constant function. That's the acceleration graph. This is position, velocity, and acceleration. It should make sense that acceleration is constant on Earth, right? Now, on Earth it's not 2, it's 16 in the downward direction for in feet, and what is it? I mean 32 feet per second squared, and what is it, 9.8? So find the acceleration of the particle when, right? Acceleration is v prime, which is s double prime. The acceleration at 4 is the first derivative of velocity at 4, which is the second derivative of position at 4. And remember, the acceleration function in this example was constant, and it was constantly 2. Don't forget units. Meters, not per second, but per second squared. Now, using the graphs, describe. And describe means yep, the motion of the particle. So I'm actually going to go to a picture of what I wrote so I can talk and not have to talk and write at the same time. So if you advance the screen, there's my first, there's a picture of what I've drawn. I know I have different colors on this one. I switched my red and green, but if you look, this is what what I had talked through. Right? When I found my -4 meters here, it was that told me the particle was 4 units left of where I started. This was an average velocity or a slope of the secant on the green parabola from 0 to 4. Instantaneous range was the slope of the tangent and was positive, right? And if you look at 4, right, if you look here, wouldn't the slope of the tangent be a positive number? And then the acceleration was constantly 2. But here's what I want to talk about. Using your graphs, describe the motion. So here's what AP wants from you. What was going on at the start? The problem told me t was 0. The particle is at a position of 3 meters. I read that from the green graph. That was right here. The next thing that was happening was from 0 to 2. So from 0 to 2, the green graph is going down, right? Whoops, look at that, I didn't draw my, I didn't capture the blue graph here all the way down. So from 0 to 2, velocity was negative, but acceleration was constant, and it was constantly positive. That was all happening from this time period. So the next thing that happened was from 0 to 2 seconds, the velocity was always negative on 0 to 2, the acceleration was always positive. Therefore, what was going on? The particle, because the velocity is negative, the particle is moving left. Because velocity was negative, but acceleration was positive, those forces are working against one another. Therefore, if they're working against one another, you're going to be slowing down. Then what was the next event? The next event was at 2 seconds. How do I know it was an event? Well, I know the position was -1, but something happened to velocity. Velocity was negative, but now it's 0. Who cares what the acceleration is doing? Is the velocity is 0, the particle is at rest for just that instantaneous second. What's the next event? The next event, once we were past 2, the velocity was no longer 0, the velocity changed to positive, meaning the particle was moving right. The acceleration is still positive because it was constantly positive in this case. But since now velocity is positive and acceleration is positive, forces are working together. Up here, remember the forces were against one another? So you're slowing down. Here the forces are working together. They're both positive. Therefore, I'm speeding up. This is the kind of conversation that AP wants when they ask you to describe the motion. Now I said using your graphs, and so we had a picture of this. I hope you can see all of this is what's going on, but You're also going to need to do these from equation, have the equations, look at the graph, and then answer those questions. Now the next thing I asked was, at what values of t does the particle change directions? There was only one event where that happened, and that was when, on this, from time being 0, and that's when time equals 2. And how, when they are going to ask you to justify that, you cannot say, I looked at the graph, the green graph turns around. That is true, and I'm glad you're looking at the graph, but on a calculus test, they're not going to accept that. And that's in the directions of the AP exam. What they want you to say is, I looked at the velocity, and the velocity changed. In this case, the velocity was negative, and the velocity changed to positive. And of course, the velocity was 0. But more important, in between there, but more important, the velocity changed from negative to positive, meaning the position graph changed from going down to going up, and in a continuous function with these are, if you change from going down to up, or your derivative changed from negative to positive, you must have changed direction. So of course I see that right here. I see that here, but you need to understand that a calculus test is going to ask you for looking there, yes, but talking about the velocity being negative and then the velocity changing to positive, which corresponded to your graph going down and then your original graph going up. This is a cool visual here, so I gave you directions. I'm not going to go through it. It's a nice visual of watching. That position graph is a parabola, but that's not what the particle looks like. It looks like it's going, right, in a straight line and changing directions in a linear fashion. So this is just a nice picture you can make your calculator give you. But that's it. Have fun doing your homework. Tomorrow I will check the homework that I assigned on Friday and the homework I assigned for tonight. See ya!